One of the main differences between stellar orbits and planetary orbits is that planets orbit in a Keplerian potential, where the orbits do not precess. The argument of pericenter is constant because the Hamiltonian does not depend on the angular momentum. The same is not true for the NFW dark matter halo potential, so the orbits precess. What you're looking below here are some examples of orbits for equal energy but different angular momentum. The motion is bound between constant apocenter and pericenter, but the orbits are space-filling. Any location between pericenter and apocenter will be visited by the star. Let us understand this behavior. Consider this Hamiltonian, which is for a central force where the potential is spherically symmetric. Since this does not depend explicitly on time, the Hamiltonian is constant and is equal to the energy. Let's then isolate R dot, equating here the Hamiltonian with the energy E. Let's substitute dot phi by the angular momentum and take the square root. So this is the equation for R dot, depending on energy, the potential, and the angular momentum. So R dot is dr dt. Let's now isolate the dr and dt. So we write this equation here with dt on the left-hand side and dr on the right-hand side. And we can integrate this equation to find the radial period. The radial period is the time that an orbiter takes to go back to the same radial position. For example, if an orbiter starts here, it's the time that is going to take to go back to the same radial position. Notice that it's not the same location because the orbit is precessing. So the same radial location may be located at a different angle. So this period, the radial period, is equal to twice the time that the orbiter takes to go from the pericenter, R min, to apocenter, R max. It's integrating here this orbit from pericenter to apocenter multiplying by 2. If the orbit is symmetric, should be the same time. So that defines a radial period. We can check that what is the azimuthal drift that occurs within this radial period, and that's going to give us the precession. So we can find that the infinitesimal azimuthal angle that is swept during an infinitesimal change in radius. For that to go back to the definition of the angular momentum and multiply both sides by dt, we have here the L, the angular momentum is constant, and we can divide and multiply the right-hand side by the r and substitute the dr, which is given by the equation above here. So I have this equation here for the phi. Integrating it again from pericenter to apocenter, then we find the angle that is swept during a radial period. So this is the angle between two pericenter passages. If this angle is not a multiple of 2 pi, then precession happens. In general, the angle between two pericenter passages drifts. Indeed, the trajectory is only closed if we have that d phi over 2 pi is a rational number, m over n, where both m and n are integers. Now, in general, delta phi over 2 pi is not rational, and a typical orbit will resemble a rosette. So this is a typical orbit in a dark matter halo potential. In fact, the only two potentials that lead to closed orbits are the Keplerian potential, which is 1 over r, and the harmonic oscillator potential, which is proportional to r squared.